We're now well positioned to state Johnson's algorithm in its full generality. The input, as usual, is a directed graph G. Each edge has an edge length C sub B. It could be positive or negative. The input graph G may or may not have a negative cost cycle. As usual, when we talk about solving a shortest path problem, we mean that if there is no negative cost cycle, then we have no excuse, so we better correctly compute all of the desired shortest paths, in this case between all pairs of vertices. If there is a negative cost cycle, we're off the hook. We don't have to compute shortest paths, but we need to correctly report that the graph does indeed have a negative cost cycle. Step one is the same hack that we used in the example. We want to make sure that there's a vertex from which we can reach everybody else. So let's just add a new one that by construction has that property. So we add one new vertex, a little s. We add n new edges, one from s to each of the original vertices, and each of those new n edges has length 0. We're going to call this new bigger graph G prime. The second step, just like in the example, is to run a shortest path computation using this new vertex S as the source. Since the graph G in general has negative edge costs, we have to resort to the Bellman-Ford algorithm to execute this shortest path computation. Recall that the Bellman-Ford algorithm will do one of two things. Either it will correctly compute the shortest path distances that we're after from the source vertex S to everybody else, or it will correctly report that the graph it was fed, namely G prime, contains a negative cost cycle. Now, if G prime contains a negative cost cycle, that cycle has to be in the original graph G. The new vertex S that we added has no incoming arcs at all, so it certainly can't be on any cycle. So any negative cycle is the responsibility of the original graph G. Therefore, if Bellman-Ford finds us a negative cost cycle, we're free to just halt and correctly report that same result. So from here on out, we can safely assume that G and G prime have no negative cost cycle, and therefore that the Bellman-Ford algorithm did indeed correctly compute shortest path distances from S to everybody else. As in the example, we are going to use these shortest path distances, all of which are finite by construction, as our vertex weights, our P sub V's. We then form the new edge lengths, the C primes, in the usual way. C prime of an edge E, going from U to V, is the original length CE, plus the weight of the tail P sub U, minus the weight of the head P sub V. In the example, we saw that the new edge length C prime were all non-negative. We will shortly prove that that property holds in general. If you define your vertex weights in terms of shortest path distances from the new vertex S to everybody else in this augmented graph G prime, it is always the case that your new edge lengths will be non-negative. Assuming that for now, it makes sense to use Dijkstra's algorithm n times, once for each choice of the source vertex, to compute all pairs shortest paths in the graph G with the new edge length C prime. In a particular iteration of this for loop, say when we're using the vertex U as the source vertex, we're going to be computing n of the shortest path distances that we care about from U to the various n possible destinations. And let's call those shortest paths computed by Dijkstra in this iteration d prime of U comma V. So perhaps you're thinking that at this point we're done, right? We transformed the edge lengths using reweighting to make them non-negative, and as we know, once things are non-negative, n Dijkstra's and you're good to go. But there's one final piece of bookkeeping that we have to keep track of. So the shortest path distances that we compute in step 4, these d primes, these are the shortest path distances with respect to the modified costs, the C primes. And what we're responsible for outputting is the shortest path distances with respect to the original lengths, the C's. But fortunately, there's a very easy way to extract the true shortest path distances from the D primes, from the shortest path distances relative to the modified costs. We know the D primes are wrong. They're computed with respect to the wrong costs, but we know exactly what they're off by. So the D primes are off by exactly P sub U minus P sub V amount. So to go from the D primes back to the shortest path distances that we really care about, we just need to subtract that term back off. And that's step 5. That completes the description of Johnson's algorithm, which in effect is a reduction from the all pairs shortest path problem with general edge lengths to n+1 instances of the single source version of the problem, only one of which has general edge lengths, n of which have only non-negative edge lengths. Analyzing the running time of Johnson's algorithm is straightforward. Let's just look at the work done in each of the 5 steps. In step 1, we just add one new vertex and n new edges, so that takes O of n time to accomplish. In step 2, we run the Bellman-Ford algorithm, so we know that takes O of m times n time. In step 3, we have to compute the modified costs, but given the shortest path distances computed by Bellman-Ford, that's constant time per edge, or O of m time overall. In step 4, we run Dijkstra's algorithm n times, and the running time of one invocation is m times log n. In step 5, we do constant work for each choice of u and v, so O of n squared work overall. So you can see that step 4 dominates, and the running time is equivalent to n invocations of Dijkstra's algorithm m times n times log n. As usual, when discussing graph algorithms, I am thinking about the graph as at least being weakly connected. I'm thinking of the number of edges m as being big omega of n. So why is this running time so cool? Well, 2 reasons. The first reason is that for sparse graphs, this solution blows away the previous algorithms that we had that could handle negative edge links. The 2 previous solutions that we knew that you could use with graphs with negative edge links were either run Bellman-Ford n times or use the Floyd-Warshall algorithm. And in sparse graphs, where m is big O of n, both of those solutions run in cubic time, O of n cubed time. This solution for sparse graphs, when m is big O of n, is O of n squared times a log n factor. So it's way better than either using Bellman-Ford n times or using Floyd-Warshall. The second reason this running time is so cool is that it matches the running time we were getting already in the special case when edge lengths were non-negative. So this is very different than how we were conditioned to think about the world when we talked about single source shortest path problems. Remember, in those problems we have Dijkstra's algorithm, which only handles non-negative edge lengths but runs in near linear time, and there's no algorithm known for single source shortest paths that's near linear that can handle negative edge lengths. The Bellman-Ford algorithm certainly is not near linear running time. That's big O of m times n. Johnson's algorithm shows that while negative edge links are indeed an issue, they can be handled in one shot using just one invocation of Bellman-Ford. While the Bellman-Ford algorithm is indeed quite a bit slower than Dijkstra's algorithm, it's only roughly a factor of n slower. So one invocation of Bellman-Ford doesn't change the overall running time when we already have to do n invocations of Dijkstra's algorithm, even in the special case of the problem where all of the edge links are non-negative. So that is why for all pair shortest paths, we see a convergence in the performance of algorithms that solve the problem in general and algorithms that only solve the problem in the special case of non-negative edge lengths. The missing piece to the correctness argument is understanding why, in general, the modified edge links, the C'E's, are guaranteed to be non-negative. We saw that they were non-negative in a specific example, but we have not yet proved it in general. We'll do that on the next slide. Assuming for the moment that that is true, that the modified edge links are indeed non-negative, and therefore when we invoke Dijkstra, it will correctly compute shortest paths, we're pretty much done. In particular, recall that we had a quiz in the previous video where we analyzed the ramifications of reweighting. And we saw that if you reweight using particular vertex weights, some p sub v's, then for a given choice of an origin u and a given choice of a destination v, every single uv path has its length changed by exactly the same amount, by a common amount, namely the difference between u's vertex weight p sub u and the destination v's vertex weight p sub v. So that means when we invoke Dijkstra's algorithm in step 4, it indeed gets the shortest paths correct. The shortest path distances are incorrect, but we know exactly how much they're off by. They're off by pu minus p sub v, and that is corrected for in step 5. So that's why assuming correctness of Dijkstra's algorithm, which in turn relies on non-negativity of the modified edge lengths, the end result of Johnson's algorithm is indeed the correct shortest path distances. To finish the analysis of Johnson's algorithm, all that remains is to prove the following claim, which is that for every single edge of the graph, its length after we do reweighting is non-negative. So the proof, in fact, is not hard. It follows quite easily from properties of shortest path distances. So fix your favorite edge, E, let's say going from U to V. The vertex weights are, by construction, just shortest path distances from the vertex little s, where remember s is the extra source vertex that we added to the original input graph G. So by the way we constructed the graph G prime, there is at least one path from this auxiliary source vertex S to every other vertex. So there is some shortest path from S to U. Let's call it capital P. By definition, the length of capital P has to be little p sub u. It's a simple matter to obtain from this path capital P, which goes from S to U, a path which goes from S all the way to V, namely just concatenate the edge UV as a final hop. The length of this path, which goes from S to V, is of course just the length incurred going from S to U, which is just P sub U, plus the length of the final hop, which is just the length of this edge, C sub UV. Now this is just some old path from S to V. The shortest path from S to V can, of course, only be shorter. And remember, P sub V, the vertex-weighted V, is by definition the length of a shortest path from S to V. And now we're good to go, because the modified length of this edge C, that is C prime sub E, is just the difference between the right-hand side of this inequality and the left-hand side. So that's why the difference is guaranteed to be non-negative. Since this was an arbitrary edge, it holds for all of the edges. That completes the proof and the analysis of Johnson's algorithm.